क्या कर पता है? One, one, two,
Yeah.
one, two,
So,
three.
Mr. Sorabh Gupta is an IIT Delhi alumnus, and he's completed his MS in Civil Engineering from Stanford University in 2004. So, Mr. Sorabh started his career with Fugro West in California, where he worked on several major projects in US, Africa, and Mexico for a period of 3 years. Then he moved to India in 2007, and after a short stint at Haley and Edridge in Boston, and joined in Cengrs Geotechnica Private Limited. And in the past 18 years, he has been actively involved in several major geotechnical exploration programs across India, and he is currently the director at Cengrs Geotechnica Private Limited, which is a leading firm in geotechnical applications and exploration. Uh, Mr. Sorabh is active in various professional organizations also, including DFI, IGS, ISSMGE, BIS, and he has served on IGS Delhi Chapter Executive Committee. To Mr. Sorabh Gupta, who will be delighting us with his pursuit of knowledge. Over to you, sir. Sir, somehow I could not get your audio. Okay.
Is that better? You can hear me now?
Yeah.
Ah,
We can hear you.
okay. Sorry. So, namaskar, and thank you so much for inviting us, Dr. Parihar. It's really a privilege to speak at this forum. I think the model would be we have two separate presentations. The first one I would be taking, and maybe with questions, it could go up to an hour. Subsequently, Dr. Abhishek will be taking the second part, which will be focused mostly on CPTs. So, before I start, may I understand who we are speaking with? Is this largely faculty and students, or is it also practicing engineers?
It is a mixed one, sir.
Mixed
There
one.
are students, research scholars, and also the
Yes.
members of the IGS who have joined.
Fantastic. Fantastic. So, with your permission, sir, I'll jump right in, and
Sure, sir.
yeah, thank you. Okay, so this time, and at IGS Shimla, I remember, I think, was it a year or year and a half back, we had done a very nice series where we had gotten into details of some of the specific tools which are
Yeah,
available on the
we
latest
have done in
technologies.
2023.
2 years back. Okay. So
Yeah.
today I decided we'll touch a very simple topic. I just wanted to zoom out and I wanted to discuss with all of us why we even need geotechnical investigations and what are the tools which are available to us. So consider this to be a very broad introduction as to why geotechnical investigations and studies are important and what they mean for the practical construction industry. Right. So we'll get into this. I'm Sorabh Gupta, I'm director at Cengrs. And let's see. So today we will talk about this. We'll talk about why we need to have good geotechnical investigations. What is good geotechnics? We'll touch upon some of the latest tools which are available for investigations. I'll show you some case studies to tell you how a good or a bad investigation program can make or break a project. And then maybe we can take some questions. So the first question is why, right? I mean, why is geotechnical so important in the industry? So let's understand any project which you have, the foundation cost is the largest variable cost or risk factor. And typically these days, the foundation cost will be roughly around 10 to 15% of the capex or of the total project cost. Now, this is huge because the margins, especially on EPC contracts, the margins are very tight. So people are competing for the same projects, and if you can understand foundation design and if you can optimize your foundation design, then that is the only way in which you can not only make money, it's also the only way in which you can avoid a lot of risk. So the superstructure is pretty much predictable, right? I mean, the cost and the time it might take to build your superstructure. The variable element on any project is only the subsurface. And what decides the subsurface? What decides this foundation cost? It is nothing but the output of the geotechnical investigation program. How much to be spent on this, right? So the international standard is you're supposed to budget around 2 to 3% of a project cost for ground investigations. The reality in India is we are spending most projects, people are investing less than 0.2% of the project cost in investigations. And this is the result of this is that we have a lot of delays in our projects. So there's cost overrun, there's time overrun, sometimes there is foundation distress, and at times there is catastrophic failure. There was a study by the NHAI, which is the apex body responsible for all the highways in the country. And there was a very interesting study by the Government of India in 2019, where they showed that 57% of the highway projects in the country, the delay in the project was attributed to suboptimum feasibility or geotechnical investigation reports. And we look at this is, and if you calculate, what this means in terms of cost to the government, that's huge, right? So every delay is cost. We have been talking about this, and I think as civil engineers, we read papers, and I find personally, I'm heartbroken when I come across news. I look at a lot of bridges which have collapsed in Bihar in the recent uh, couple of years, and it's become almost so common that now we don't even react to news like this. We had seen, if some of you might remember, 2019 there was a building collapse because of a metro construction in Calcutta. This is a retention system collapse. Incidentally, in NCR, we have had at least 2 or 3 retention system failures only in the last 1 month, right? And that is what we are talking about. So these stories about collapse and foundation failures have become very common. It makes bad news. It makes civil engineers, Indian civil engineers, look bad, and it's completely unnecessary because the only reason for this is our own apathy and our own lack of knowledge. I love this quote by Professor Littlejohn. He says that you pay for site investigations whether you do it or not. Karo ya na karo, you have to pay for it, one way or the other. If you read the papers, you are reading about this very recent, this is a couple of weeks ago, there was a huge RE wall failure in Kerala. And we are in conversation with NHI as we speak. In fact, we are part of the committee where we are trying to now rectify the issues and see what we can do about this. But you look at this, I think if this is a textbook case of bearing capacity failure, it's completely avoidable. I think the reason for this, it wasn't RE wall construction. The reason was, I think the investigation of the subsurface wasn't done properly. It wasn't correct, and they overestimated the weight that the ground can take, because of which, when they constructed this 9-meter high RE wall, the entire thing collapsed. Right. So I won't go through this much in detail, but this is just to give you a sense of logic. So this is a study by NCRHP. On the y-axis, you have the percentage increase in project cost. On the x-axis, you have the percentage investment in ground investigations as a percentage of the overall project cost. So obviously, this is where we are in India, right? I mentioned that we are standing at investment levels are at 0.1 to 0.2%. So obviously, if you don't study the ground well, then very likely that you will have some escalations in the project time and cost, right? And ideally, this is where we ought to be. The global standard says that this is where we should be putting all our money and our effort at the beginning of the project during the design stage, so we don't get surprises and delays during the construction stage. It's a simple logic. Right? Unfortunately, uh, practically in India, and we've been doing investigations for the last 35 years, uh, particularly for smaller projects, the story is very different. So when you meet the customer, it's almost a negotiation. They want to negotiate, they want to reduce or eliminate investigations if they can, or minimize investigations. They want everything done fast. They don't care about the quality of the work. And all of this, this kind of a scenario. And unfortunately, on the other end of the table, you have enough uh, geotech consultants who are willing to accept these kind of conditions and give a report without doing a proper investigation. So this is really the root cause. This kind of scenario is a root cause for many of our problems. And I think as students, if when you're learning and when you're graduating, you have to put this into your mind that this is when you go into the industry and you see these practices, you have to understand that this is not right and you have to fight against this. The Indian scenario is poor in the sense, although it's improving, but slowly. But right now, I would say it's still poor in case of a lot of our standards are still outdated. A lot of specifications are obsolete. Uh, Awareness of good geotechnics, I think, is very low. And this is amongst all stakeholders. So owners, designers, structural consultants, architects, uh, even within the geotechnical fraternity, awareness of good geotechnics, I think, is very limited, and that's what we are trying to change. Through opportunities like this. There are very few good investigation companies. I would peg it at less than 1% of the total number of companies are actually good companies which are doing authentic data. Many companies are out there, giving inauthentic data, giving inauthentic reports. They may not be carrying out all the tests and they're just fabricating reports. The other gap is we don't have proper standalone geotechnical design companies in India. Mostly we have suitcase consultants, but good size professional geotechnical design companies are still missing. L1 procurement practices from the client end are always a problem. And I think the impact of this is the time and cost overruns of our projects. So many projects. So these days, every year, we'll do dozens of projects which are forensic in nature, just like the Kerala project. The failure has already happened. Something's gone wrong. Piles have failed. Buildings have toppled. And after that, they bring in the geotech consultant to come and do a forensic investigation to figure out what went wrong. Now, this is always a bad idea because you're going to end up spending a lot more. You are absorbing risk in your project, and your time delay is going to kill your project. So, it's always a bad idea. And on the other end of the spectrum, most of our other projects which are not falling down, uh, it's likely because the design is over conservative. Right? Now, conservatism is not good engineering. Conservatism is leaving money on the table. It's lazy engineering. Correct engineering is you have to be correct. You can't be over conservative. You can't be risky. You have to be just right. You have to be right where the money is. So that is good engineering, and that's what we are trying to get to. So, what is good geotechnics? I always like to start with this simple diagram, and I think it makes sense. See, if you look at the medical profession and how the medical profession has improved over the years. So, when I was young, when I was a child, I remember I used to go up. हम लोग डॉक्टर के पास जाते थे कुछ भी हुआ है and the doctor used to check blood test blood pressure fever and give a few medicines, right? Uh, so that was very simple, almost subjective, or I would say very empirical way of practicing, right? So that is how it used to be. Similarly, in geotechnical investigation, we have some very conventional, simple, easily available tools like your borals, your DCPT, plate load test, uh, and that's sometimes it's good enough if the symptoms are not very strong. But if you have with advancements in medical technology, with advancements in engineering, now if you have some more serious kind of symptoms, then you go to a doctor. The doctor is going to do some advanced tests, right? Or maybe you have to go for a CAT scan, MRI, something. Same way, if your project complexity is slightly more, right? If you're building something which is a larger structure or you're building in complex geotechnical scenario, subsurface conditions, you have to up your game and you have to move to more advanced testing methods so that your decisions your foundation design decisions are based on data, not based on feeling or not based on just your subjectivity. And this is where, good geotechnics comes in. So with this in mind, we developed recently, a couple of years back, we developed this kind of a pyramid, right? And I'm not going to go through this in detail. You should understand the gist of it, right? So at the bottom of the pyramid is the bronze level. Bronze level bole that if you are building, say, a simple structure, maybe a G+2, G+3 building in an area where the geology is competent and it's fairly well known. In that kind of a scenario, it's okay to just do a basic investigation. You could do a couple of shallow borings. You could do a little bit of lab testing. A lot of your analysis could be empirical, semi-empirical, based on your, experience in the area. And maybe even if your values, your SBC values, are a little conservative, you are okay because the cost of investigations is less, but you are fine. Okay, but that's really the only area where this is acceptable. However, as your projects become more complex, maybe you're building tall buildings, power plants, refineries, as your project complexity increases and or as your ground conditions become more complex, maybe you're dealing with a highly seismic area, maybe you have liquefaction potential, you have shallow groundwater table, you have soft ground. As these things happen, you have to move up the value chain and the level of the geotechnical input has to improve. Right. In a gold level, for example, what we typically do, and these days we do this a lot, is a gold level investigation means that I am going to come, maybe I have a staged investigation, maybe I combine my conventional boreholes with advanced in situ tests like CPTs, pressure meter, cross holes, so on and so forth. So I can have a better ground characterization. Right. And by doing that, and maybe I improve my analysis part as well. I improve my analysis by maybe looking at softwares. I do FEM analysis. I can do some complex analysis, so on and so forth. Now, the reason for going up the value chain is as you go up the value chain, your strength reduction factors will improve. Your cost of foundation is going to reduce. And also your time of foundation construction will also go down. And that it's very obvious that is how it works. And I'll show you today a few case studies on how we achieve this in practice. So with this in mind, let's just touch upon what are the areas of improvement. I think everything starts from awareness, right? And so sessions like this, interaction like this is how we all build awareness. We share from each other's experiences. We learn from each other's mistakes. And that's all about awareness, right? And that's number one. The number two is obviously the selection of the geotechnical consultant. That process has to be, once you're aware, you'll automatically choose the best consultant, not the cheapest. Just the same way these days we are very aware about medical sciences. So all of us want to go to the best doctor, get the best test done. And we are not looking, if I'm unwell, I will not go to the cheapest doctor. I'll go to the best if I can afford it. Right. Data reliability, I cannot overemphasize this. This is very important. A lot of students these days, it's become fashionable to, just do your thesis with softwares. Softwares are great, but what you have to remember is that the data, the input data which goes into a software, that is the key. Right? If you don't understand where the input data comes from or which input data to use, you are simply doing garbage in, garbage out, and softwares will not help you improve your design. So data reliability is, I think, a very important step. Sorry. Defining the SI scope. So if you have a project, you have to define the scope of the geotech investigation. It cannot be a copy-paste job. The effort must be made by all the stakeholders, structural engineer, architect, geotech consultant. Everyone should sit down together, discuss what is being built, what are the likely challenges at the ground, and should define the scope of the investigation in such a way that we get all the inputs we need at the time of design, and so there are no construction surprises. Selection of SI tools is very important. As I said, you have to customize this. You cannot just do borings everywhere. Depending on the site, you have to choose the tools that you have to use. So we can come up with some kind of a risk-based flowchart for site characterization. Again, very similar to the bronze level. If you have a low-risk project, you can do a simple bronze level investigation. But as your project complexity or risk levels go up, it is important to tailor make your SI program. So you may have to do a staged investigation. Maybe you do a preliminary ground investigation, get a little bit of data. You may have to follow up with in situ testing, detailed investigations, site-specific correlations, lab testing, so on and so forth. So there's stages, and this is the flow chart has to be defined early on in the project, so we know where we are headed. So we talked about why investigations or good geotechnics is important. We talked about what good geotechnics is. Now let us look at some of the tools. Uh, this is a slide also by Professor Main, and I love this slide because I think particularly in India, if people talk about geotechnical, they think about boreholes, right? And we want to change this because I think it's time. Boreholes were not are good in their own place, and the strength of borehole investigations and SPT is only in the fact that it is cheap, it is easily available, and we are comfortable, we are familiar with it, right? But that does not mean that boreholes are enough. Over reliance on SPT end values is not good. SPT stands for standard penetration test, but I think we all know there's nothing standard about the SPT value. It depends on all of these parameters. And very honestly, if you do SPT at the same site, if you do it maybe at two different locations of two different companies are doing it, chances are the SPT values are going to be very different from each other, right? So it's hard. Borehole investigations, I feel, are hard to get it right. It's a very manual, slow process, uh, and there are many uncertainties, many sources of error. So it's very hard to get borehole data right. And you have to remember, it's not just SPT, it's sampling, the way you collect the samples, the way you transport them, the way you do your lab testing. Uh, you have to be very, very serious, and you have to have a very robust process to get this right. Keep in mind also that in boreholes, really the output of what you get, a lot of the interpretations that we have based on borehole data are going to be empirical and based on judgment. Right? So it is very important as India moves forward. I think a paradigm change is required in the way we carry out geotechnical investigations. 20 years back, when I started my career in the US, even at that time, I remember they used to do very few good quality boreholes, and they used to do a lot of in situ tests for all kinds of projects. And it's taken us in India, unfortunately, 20 years to get to that stage. But nowadays, when we do investigations, the things are changing. We are doing fewer boreholes, and we are depending more on in situ testing. Speaking of boreholes, let's understand standard penetration test because this is here to stay. I don't think the SPT is going anywhere. You will need this on many project sites, largely because of its ease. It's easily available everywhere, right? So let's see how to get SPT right. I would talk about two things, or rather three things. The first is you have to remember the weight of the hammer has to be calibrated. Second is, anytime you see a borehole report, you have to go back and ask the agency if they have used an automatic trip hammer. Why an automatic trip hammer is important is because if the height of fall of the hammer is not consistent, your N value is incorrect, right? So IS 2131 incidentally has been published this year. It also mandates the use of an automatic trip hammer system. Many kinds of SPT arrangements are there, but I think having an automatic trip system or release system is very important. The third thing which is very important and which has also come up, if you look at the books, if you look at valves, the N value is always written as N60. N60 means 60% of the potential energy is being transferred to the ground. Now, you don't know if it is 60% if you don't measure the actual energy transfer ratio. So how do you measure it? You use an equipment like this. It's called an SPT analyzer. So what this does is you have an instrumented rod, which is placed here in line with the SPT equipment. It's got accelerometers and strain transducers built into the rod. So when you actually carry out the SPT, this equipment will measure what is my energy transfer ratio. So the ETR value, once you know, you can correct your measured N value to N60 value. Why is that important? Supposing I have a site where my SPT N value is 10 and I assume a 60% ETR, I'm going to calculate an SBC value of 100 kPa. Right? But in most cases, if you use an automatic trip hammer, we have seen that the actual ATR is around 75-80%. What that means is the N value of 10 was should be corrected to a value of 13. That means your actual SBC value is not 100 kPa, it can be bumped up to 150 kPa. Now, 50% increase in your bearing capacity value, you can imagine the amount of cost saving that the customer can get. On the other hand, if we actual ETR value is 40%, that means my 100 kPa value was incorrect and risky, right? And it should actually be around 75 kPa. So, irrespective, the takeaway is SPT energy and automatic trip hammer should be mandatory for all investigations done using boreholes. This is changing these days. We are also pushing to have it changed in the specs. But we have to remember that these two things should be made mandatory. If you look at rock drilling, what I want to explain to you is if you have a site and like in Shimla also you have a lot of rock, you have to remember that most of the geotechnical design is done based on core recovery and RQD values. Now, core recovery and RQD is, you have to remember, is also a function of the tools which are used during investigation. So if you're using a calyx kind of a drilling machine, or if you're using single tube core barrel, what will happen is that your rock core in situ might be a solid rock, but because of the sample extraction process, if there is vibration in the machine or if the tools are not good, then those cores will break while they're coming out. So when they come out, you will look at the rock core and you feel, oh my God, my rock is highly fractured. I should probably use a very low SBC value for design. Right? Whereas the issue was with the tool, not with the rock formation. So using these kind of proper hydraulic drilling rigs is very useful because here, this is the amount of difference it makes, right? So this is a site in on the river Tapi, which we did a couple of years back. So the customer had done a soil investigation work report. They already had one. The design was already finalized. As per the report, the core recovery values were in blue. They were very low. The RQD values are very low. And basis that, they designed these huge footings for the bridge. Uh, Unfortunately, when the contractor went to actually do the construction and they started the excavation process, then the contractor complained that the rock was very hard, which was not expected. So the work got stopped. They were unable to excavate. So they called us in. We went back with a hydraulic rig with triple tube core barrel. We did some confirmatory investigations and we realized that the actual core recovery values were very high. Right? They were not these blue values, they were the pink values. The RQDA values were also much higher. And what when we redesigned the foundations, we realized that the impact of this exercise was that we could redesign, we could reduce the size of the foundations, we could reduce the depth of the foundation. And just for an investment of 15 lakhs, the customer managed to save almost 2 crore rupees only in the foundation cost saving, let alone the time saving. So that is the power of good geotechnics. All it takes is awareness. It doesn't take money. It doesn't cost much to have these kind of savings. You only need to be aware of what is the right thing to do. So I'll recap with SPT, automatic trip hammer and energy measurement is mandatory. If you have rock and you are coring in rock, insist for a hydraulic drilling rig with a triple tube core barrel. Right? And that is the industry standard as well. The third thing, even in conventional borehole investigations, is make sure that the laboratory is well equipped. It has sufficient equipment, sufficient technicians to be able to handle the amount of testing that is required. Right? I cannot overemphasize this. Unfortunately, a lot of investigation companies are not doing the lab testing. They're simply, taking the samples, doing a few tests, and fabricating the rest of them. And these kind of spurious reports are creating a lot of issues in the industry. So we have to be sensitive. We have to be aware of this. We have to know, as a good geotechnical engineer, we have to know how to assess a laboratory for its capability. Another side, and remember I told you that GTI is not just about boreholes. So these are all the tools which are available to us. Many of these tools, until around 10 years back, were not present in India, but these days I'm happy to say several of these tools are available with us, with a lot of companies, and we must learn about these tools and we must learn which tool is good for what kind of ground conditions. So of these, I want to just give you a quick introduction on a few tools. The first one is the electric cone penetration test with pore pressure measurement, also known as the CPTU. And I think Dr. Abhishek will talk about this in detail in the next presentation, but I'll just introduce you to what this is. So rather than doing so, in I think around 60 or 70 years back, they invented the CPT cone was invented. So this is an electric cone, a piezo cone. This is known as. It has got built-in sensors for measuring the cone tip resistance, measuring the sleeve friction, the pore pressure, depth, inclination, and sometimes even geophones and other things, right? So this is the cone. The cone, there is no borehole involved. Directly you take the cone and the cone can be pushed into the ground. And as you push it into the ground, you get this data in the laptop. You get the cone tip resistance, you get the sleeve friction, and you get your pore water pressure. Let's compare in terms of boreholes versus CPT. So, and I'm giving you advantages. How the test is done, Dr. Abhishek will cover. The first benefit of CPTs and the greatest benefit is time, right? So, one borehole to 30 meters, by the time you do the sample correction, you take the samples back to the lab, you do the lab testing, you get a report in around 20 to 25 days' time. In a CPT, it's very quick because it's a digital technique. You just have to push the cone down. So you can do a 30-meter test in and get the report in just about 3 to 4 hours time. So that's huge, right? So, because that means you can collect a lot more data for a lot less money and in a lot less time. Right? The second comparison is that whereas borehole data is, you're doing SPTs every 1.5 meters. So sometimes what happens is you might miss a few layers in the ground, right? And that becomes a surprise later on during construction. In a CPT, because it's digital, you are taking data continuously and your data resolution is 1 centimeter. So you have a data point every 1 centimeter. Even if I have a thin seam in the ground, I can catch it with the CPT, which I will definitely miss using a borehole. Boreholes are manual data collection, it's analog, so a lot of sources of error, human errors, transcription errors, so on and so forth. CPT, because it's digital, human beings are not involved. As long as the cone is calibrated and you just push the cone, irrespective who's doing the CPT, who's the operator, who's the company, what is the kind of tool which you use, you will get this exact same data every time. Uh, so having digital data is good because you get repeatability, you get reliability, and also because there are no sources of human error. So there's no transcription error. There's this file which is created, the file is imported in the software generates a report. So because of this, obviously reliability of the data is very high. The last point is that CPT is very versatile as well. So in a borehole, typically the only field measurement which you are getting is typically the SPTN value. Whereas if you're doing a piezo cone test, you're getting all these measurements at the same time. So you can get your cone tip resistance, friction ratio, pore pressure. You can also stop the cone, do a dissipation test. You get the T50 values, which will give you an idea of your consolidation and permeability values. And if you're using a seismic cone, you can also test for the shear wave velocity profile at the same time. So much more versatile. And all of this, the most interesting part is these days, at least at Cengrs, what we did is post-COVID. Earlier, we used to have CPTs in India, but they used to be very expensive. Post-COVID, what we did is we got the cost of CPT down to the same as the cost of boreholes. So now, whether you do a borehole or you do a CPT, it's the same cost to the customer, whereas obviously CPT is cheaper, faster, and better. The other good news is that we've also imported CPT samplers. So what we do now is we are able to use the CPT equipment to push a sampler. This is known as a moss tap sampler. We can actually push this sampler into the ground and we can take fairly intact soil samples at any desired depth. So this is also a huge advantage of modern CPT equipment. So that's with CPT, and we'll talk more about this. The second in situ test I want to touch upon is pressure meter. I want to give you basis of why pressure meter is important, right? Let's go back to the basic concepts we all are learning or have learned in school. Uh, the so-called net allowable bearing pressure is the minimum of two criterion. The first is the bearing capacity criterion, which is the strength criterion, and the second is the settlement criterion or the serviceability limit state. Right. So the lower of these two values is the net allowable bearing pressure. In 90% of the cases, the resettlement criterion was governs. So what is important is not necessarily to know where the soil fails. So your gamma C phi Terzaghi equation, that's very good and nice, but that's not what is critical for practical design. What is critical for practical design is to understand what is the load settlement behavior here in the elastic portion at the working strains, right? So this is important to understand. And now to understand this, and particularly if you're going to estimate, if you're going to assume that the soil is linear elastic, really what's important to understand is what is my modulus or what is my stiffness of the ground. The purpose of the ground investigation, end of the day, is to define the ground modulus profile as reliably as we can. And that's where pressure meter is a very, very useful tool. If we go to France, incidentally, they use pressure meters for all kinds of buildings, and they're very much reliant on pressure meters only. They don't do other tests. How it works is you basically have a pressure meter probe like this, which is lowered into a borehole. And when you lower it, you expand the probe. It's like a balloon. तो वो गुब्बारा जब फूलता है, you expand it, you measure the pressure versus volume graph. The slope of the pressure versus volume graph will give you the in situ measurement of the ground modulus. Simple as that. So it's a very simple test. The advantage of this test is, you see this, normally, how do you get modulus values? You'll do a borehole, you'll get your SPTN values. You may or may not correct your N values to N60 or N60 CS. But whatever empirical way you correct your N value, and after you get your N value, typically you have to plug it into one of the formulas. Maybe if you use a Bowles correlation, Bowles book gives a correlation for modulus based on N value, 2.5 N plus 15. So you'll get this kind of a profile. But there are 5,000 other correlations with the SPTN value. You pick a different correlation, you might get a different ground modulus profile. So you see how if you're solely based on empirical correlations with SPTN value, your understanding of the actual ground modulus is going to be very poor because of not only the variability in the actual SPTN values itself, but also because of variability in the modulus values as interpreted from the SPTN values. So there's so many empirical correlations. Right? So the better way to do it is, so you see the line is the modulus value which you get from CPTs at the same site, incidentally. The green triangles are the modulus values which you get from pressure meter. What you must take away from this is two very important concepts. The first concept is, if you have a way of doing in situ testing, it's very likely that your degree of confidence in your ground modulus value will be a lot higher because they're direct measurements, and because usually if two different methods are agreeing with each other, that will give you a lot of confidence in your input values. Number one. Number two, in this case, if you see, at the founding level, the actual modulus value as measured from CPTs and pressure meters was 4 times higher as compared to what we were getting from correlations. What this tells us is that our actual ground stiffness is very often much higher than what we think it is, right? And what that means for all of us as engineers is there is tremendous potential for optimizing our designs in most cases. So this is key. So no matter what we do, and when we sit down to define the scope of investigations, this is where we should think is, you know what, how am I going to get not only the strength parameters, how am I going to understand the ground modulus, the stiffness parameters of my site, so I can give my customer a very good geotechnical design. So that's with pressure meter. I want to touch upon seismic testing also. This, I think, in the years to come and starting this year, this has become very, very important. And I think the next 20 years, all of you will see a lot of seismic testing happening. Why? What is seismic test and why do we need it? The Indian BIS standard, it's the IS 1893 Part 1. This has been revised last month. And now, finally, after a lot of time, I think this new standard mandates that you have to define the site class is now defined based on shear wave velocity. So for most buildings in most parts of the country, you will mandatorily have to do seismic testing in situ on the site in order to get your site class. The site class is, different classes for the site, which is used in the seismic design of the structure. So you need seismic design, seismic testing or shear wave velocity testing for uh, as per the code in order to determine the site class. So that's reason number one. Reason number two, for liquefaction evaluation, you need shear wave velocity. It's recommended to have shear wave velocity if your site is liquefiable. You can use shear wave velocity data for static analysis of foundations because you will see how you get a dynamic modulus value, which you can degrade to a static equivalent static modulus value, and that number can be used just like we had the ground modulus profile. You can also get a ground modulus profile based on seismic testing. If you have machine foundations or if you have very high seismic or wind loads, you your seismic test or shear wave velocity test will also give you the dynamic soil parameters, and that can be directly used for the machine foundation design. And I'm not going to talk about this, but in unique cases, seismic testing is also very good because it will help you understand if there is in situ cementation or aging. The only way to capture that is by doing low strain testing. This is how you can actually get. So you have a lot of options if you want to measure the shear wave velocity. There are a lot of invasive techniques. You have borehole investigations. You have ground investigations like MSW, SASW, so on and so forth. You also have some lab tests which you can do for shear wave velocity. In all of these, every test will have its own strengths and weaknesses, pros and cons. Now, understanding what test is applicable for what kind of site or what kind of application, that is the key. So very quickly, if my interest is in understanding the two-dimensional or three-dimensional changes in the shear wave velocity or profiling, maybe a ground investigation technique like MSW, SSW is very good. If my interest is to understand the variation in shear wave velocity with depth, then maybe a borehole investigation technique like a cross-hole seismic test is very good. This is what a cross-hole seismic test looks like. Very quickly, you make 3 boreholes. Uh, this is what the equipment looks like. You make 3 boreholes, you lower a seismic source in the first borehole, you lower triaxial geophones in the other 2 boreholes. When you impact the source, there is some energy which is produced and some waves which are produced which travel in all directions, and these geophones will catch it. Right? Now, obviously, velocity is distance divided by time, so you know the distance between the source and the receiver. You can measure the time from the data, and when you divide these, you will get your compression and shear wave velocity profiles. These can be converted into dynamic modulus values, bulk modulus and elastic modulus, and you can also get your dynamic soil parameter profile. So this is the output of a good shear wave velocity test. There's another option. Remember, we talked about CPTs, and again, we'll discuss seismic CPTs in detail. There's also the option, the piezo cone can also be upgraded by putting a seismic module above it. And then this is called a seismic cone, SCPTU. Seismic CPT, U stands for pore pressure. So an SCPTU test, this is the latest technology. In fact, I think we are the only ones in the private industry to have a seismic cone so far. We imported a seismic cone for the first time in, I think, less than a year back, and we're getting some fantastic results. I'll tell you why. The process is very similar to a CPT. You push the cone into the ground, except you stop the cone wherever you want to test for shear wave velocity. There's a ground source which is impacted. When you impact the ground source, the shear waves are generated, and they will travel like this, and they'll hit the cone. Right? And when you do that, again, the same thing, distance by time will give you the velocity, so you get your shear wave velocity profile. This is, so in an SCPTU, a seismic CPT, this is what the data will look like. You have all this data with single push. You will get your cone tip resistance, sleeve friction, pore pressure, shear wave velocity, and your soil type. Right? And this is the power of doing in situ investigation. So much data which you get at the drop of a hat. So very versatile. A single SCPTU test, that means, is giving you not only a soil behavior classification, it's also giving you your strength and stiffness parameters. It's giving you your consolidation and permeability parameters like OCR and so on and so forth. And if you're doing a dissipation test, you're also getting your permeability characteristics. So a lot of parameters which you get from a single test. I'm going to skip this. I think it's very theoretical. I'll quickly show you some of the others. So these were all geotechnical tests. I'll quickly show you some of the geophysical tests which are also available. If you have a site where you have varying depth of rock and you want to understand how the rock depth is varying across the site, a seismic refraction test is a fantastic geophysical test. You just spread some geophones along the ground, you use a surface hammer, and by the principle of basically by Snell's law, you can actually figure out the velocities of the different layers and you can figure out where the hard layer starts or where the rock starts. And that's what a seismic refraction test data or result looks like. I always emphasize if you're doing a geophysical investigation, you must be able to cross correlate the results of the geophysical investigation with actual geotechnical investigation results. So these two things are like brother and sister, they have to go together. You should avoid doing geophysical investigations standalone. Always correlate and double check your data before you move to the design phase. This is an electrical resistivity tomography, ERI. This is the kind of data you can get from ERI as well. Again, a very good geophysical tool, not only for profiling, but also for detecting voids and other anomalies in the ground. You have other tools like SASW, Spectral Analysis Surface Waves, MASW, also very good profiling tools and very good for getting your shear wave velocity profiles fairly quickly and fairly economically across a large site. So these were the tools, right? So we talked, I'm going to keep recapping. We talked about why, what good geotechnics is, why it is important. We touched upon some of the latest tools which we have, geotechnical and geophysical tools for getting proper authentic data. Right. Now, all of this effort, let us see practically in the industry how we have leveraged this information to benefit our projects and benefit our customers. Right. So, okay, so this is the first example. Uh, this is actually, some of you might have read about this. We are working on the India's largest wind turbine project. This is in the state of Gujarat, in a place called Khavda, Run of Kutch mein. वहाँ पे we have done investigations for 263 wind turbine generators. Wind turbine generators are those big windmill type of things which you see, obviously, which the generators which are producing electricity. So 263 wind turbine generators. The scoping given at each of these WTG foundations was boreholes and cross-hole seismic test. So the case which we made to our customer was this. We said that if you have to do, the soil condition in Khavda very poor, very soft ground, liquefiable, so on and so forth. So we told the customer that, if you are doing conventional investigation based on borings, the time of investigation for doing so much work, you will need 191 days, even with 5 drilling machines working constantly at the site. So we made a case to the customer. We said, hey, instead of doing this, why don't we switch over to a CPT-based investigation program? And if you do that, you can actually complete the entire investigation in just 38 days. That means you can save 80% time, investigation time. You can also save a lot of money. And at the end, you will get data which is a lot more reliable and a lot more robust. So your geotechnical design will also be a lot better. So this is how, remember when I said that we must think about the scope very carefully before we enter the project. This is how, if you can think out of the box and if you can use technology, this is how you can benefit the project. And the data, the results, we did this actually. We did boreholes and CPTs at the same location to illustrate to the client how you will get the same data. So we got the borehole data. Next to it, we did a CPT, and then we compared the soil type from the borehole at the CPT and matched very well. We also compared the SPTN values. So the black line is the SPTN values correlated from CPT data. The purple dots are the actual SPT values corrected for 60 at the same location. You see how well it matches. We also matched the shear wave velocity values which you get from CPT, again the black line, versus what we got from cross-hole seismic test at the same location, which is the red dots. So you see how, had we done a borehole and crosshole investigation, uh, versus what we do from CPTs, the output is the same or sometimes even better. Right? Liquefaction analysis particularly was an issue here. So we also illustrated to the client how liquefaction analysis would be a lot more reliable if you're doing it based on CPTs. So this is one case study. Same customer, different site. This is in again in Gujarat, in a place called Mundra. Right? Again, terrible soil conditions. The story here was the client already had a basic borehole investigation report, basis which the safe pile capacity theoretical was calculated as 158 tons. Right? The huge petrochemical facility, so the number of piles was 50,000 piles, and 1,000 crore was the cost of the foundation alone, 1,000 crores. So we saw this report, and when the customer came to us, and we looked at the report, and we were like, hey, number one, your borehole data does not look very reliable. It seems like the work is not being done, the lab testing has not been done properly, and we also felt that the pile capacity seemed to be over conservative. So the client asked us to do a confirmatory investigation. We went back and we did CPTs. I think a lot of CPTs, 200 or 300 CPTs across the entire site. Basis that CPT data, we re-evaluated the pile capacities, and we've got that the actual pile, we revised the pile capacity from 158 to 320, right? And that's huge because if you can justify higher pile capacity, number of piles and the cost obviously went down to half. So 500 crores is what the client could save just in the cost of the piling system. 500 crores is what they directly saved in material costs alone. And to top it all, when they actually went back and did when they installed the test piles, did the pile load tests, they found out that the actual pile capacity at site matched what we gave them based on CPT very well without being risky, whereas the original values from Boros were over conservative. Right? So another example of how you can save a lot of money for the client. And see, and this is where you have to realize that we always tell the clients that they should never look at money which is being spent on good engineering or investigation should never be an expense. It should always be looked at as an investment in the project. And truly speaking, it will always be an investment. Right? So we tell the client these days we're talking money worth. We say, boss, you forget the technical aspect. This is 500% ROI on your investment. Okay. In real estate, also, we have changed the way in which we are approaching real estates. Pardon me. So in real estate, earlier, there's so many high-rise buildings which are being built in NCR and other parts of the country. So conventionally, we used to do only boreholes even for tall buildings 10 years back. And values of 30, 34 tons per square meter were the common SBC values in NCR area. So this was another case study where similar, this is in Gurgaon. The client actually carried out a basic conventional geotechnical investigation program with boreholes. They got an SBC of 34 tons per square meter because they were building 40-story buildings. 34 tons per square meter was insufficient for raft. So they had to go, the design was based on raft as well as piles. The cost of foundation was coming out to be very high. So for 5 towers, the foundation cost was working out to be more than 20 crores. So the client obviously was panicking because they had not budgeted for so much expense. They came to us with a copy of the report. We saw the report. Once again, we felt that we could do a better job. So we went back to the site. And this time we carried out very few good quality boreholes. And we also carried out CPTs, pressure meters, and cross-hole seismic tests at the site. When we got this and we got a better idea of the ground modulus profile now through advanced testing, we managed to justify a much higher net allowable bearing pressure of 64 ton per square meter. We managed to eliminate the piles entirely, and the revised foundation cost is only 4.5 crores. So you see how if I can invest, even if the client invested 45 lakhs in the investigation program, if I can give him a benefit, if I can save 16 crores in the foundation cost, there is no one happier than my customer, and it's a win-win situation for everyone involved. Right? Another example is this. This was for a greenfield steel plant in Ludhiana in the state of Punjab. Same story. The original report was based on piling, and the foundation cost, the budgeted cost in this case was 350 crores. We went back in. We did, I think, around 125 CPTs, some 25 boros, some other tests. We managed to reevaluate, and the revised foundation cost was only 135 crores, simply because we did, in this case, the site was liquefiable. We managed to optimize the liquefaction depth. We managed to optimize the depth to which ground improvement is required. And basis that, this is the amount of money we managed to save for the client. Possibly the last example is we did a very interesting project where the client came to us and they said we have to build food grain silos in 66 locations across North India. So they came to us and we did the analysis at one location. This is Balrampur, Uttar Pradesh. Same story. Had we done, so the client had done a conventional investigation program. It took him around 46 days, cost him around 2 lakh rupees, and they got this kind of SBC and a 4 crore ground improvement cost. So we went back to them. We said, hey, not only is this over conservative, it is also taking you too much time to do boreholes, and time was of the essence. This was a very fast project. So we said, instead of doing that, let us do a two-stage investigation program. So the first stage, instead of doing 15 boreholes, we said in the first stage, we'll go and do 10 boreholes. We'll get a report. Then we'll go back, follow up with the drilling machine. We'll do 4 or 5 confirmatory boreholes, and then let's see what we get. So what we got is the investigation, because we replaced a lot of boreholes with CPTs, we could finish the investigations a lot faster. The spend on investigation was the same because cost of borehole and CPT is roughly the same. So paisa to utna hi laga. Whereas the SBC value we could justify from 7 tons, we went up to 13 tons per square meter. The depth of ground improvement could be reduced, and the foundation, the cost of ground improvement we could reduce per site from 4 crore to 3 crores. And now remember, this 1 crore is for one site. There were 66 sites. So 66 crores is what the client saved on these high-low projects simply by being open to doing better investigations and better geotechnics. And with that, I thank you for your time. I think I finished exactly on time. So hopefully we have some time for questions.
Thank you very much, sir. That was very insightful lecture. That is something you test which we don't discuss many a times. That why we
Yes.
actually need to do it and how we need to do it. I request the participants to please either post a question or you may unmute yourself to ask the questions. So, by the time the participants are there to pose their questions, I have a
Yes.
few queries of mine also. Can you please
Please, sir.
just elaborate on the case of that returning wall failure in Kerala? I think that was RE wall that was still there. Lot of discussions went in the IGS groups also.
Yes, you are right. I don't know how much I'm permitted to share, but I have a slide for everything. So would you like me to go through this since it's
Yeah,
a hot topic?
yeah. If you can
Maybe
give a
5 or
little
10
more detail.
minutes. 5 or 10 minutes. This will take. This is not so much about why the failure happened, Dr. Pariyar. This was a discussion. Actually, Chairman NHAI invited us along with a couple of other agencies recently. So Chairman invited us to figure out what we can do about it. So this is a presentation which we made to Chairman NHAI just a couple of days back. I think 10 days back. So I'll share you what we shared with them. So this is the failure, right? So as I mentioned earlier, as a typical bearing capacity failure. Problem kya tha ki the original soil investigation report here, if you see, the soil investigation report showed some very good quality soil and value of more than 20, 30 and everything. Right? Whereas obviously that is not the case. Even from the photograph, you can easily see this is soft clay. Right. So the investigation report itself was bogus, actually. I don't think they've even done the investigation. Whoever did it, God knows, they just cooked up a report. So So there was no ground improvement which was planned for this retaining wall structure. Unfortunately, these are all paddy fields, side pay. So typical Kerala. Kerala has got very soft clays. We have also done so much work there. Paddy field area, clearly soft clay. So ideally, they should have planned a ground improvement, you know, before constructing the RE wall. But because the investigation report showed that the soil is very good, they directly started constructing the retaining wall. So as they constructed it, obviously this is a very typical deep-seated bearing capacity failure which has happened. Right? Uh, so there is precedence. By the way, this is not the first time. This is happening everywhere, not only in India but also abroad. So we took out, for example, this is in Vizag. Similar thing had happened sometime back in Brazil and Canada. So this is happening very often, right? Sometimes it is. So there are two kinds of failures. Sometimes the failure is within the RE wall itself, and that could be because of poor design or poor construction. Maybe they don't use the right length of geosynthetics. Maybe they don't compact the soil properly. Uh, but very sometimes it is simply because they didn't understand the subsurface on which the structure is being placed. Right. So the lesson from this, and this is what we talked about, the lesson was, number one, the cause of failure was bearing capacity failure triggered by a rapid rate of embankment construction. Right. They didn't plan for it. There was no preloading, surcharge, no PVDs, no stone columns, nothing. Just directly soft clay pe banana shuru kar diya. So that's a classical, I mean, that's the very simple geotechnical mistake. I think even in our college, they used to teach us not to do these things. Right. Uh, so then we talked about, post-fillet investigations. For this case, we made a case that to really understand this kind of ground, what we should do, we felt that the intention is to understand the undrained strength profile. So for that, so the case we made is it doesn't make sense to do only boreholes. We said it's very important to do CPTs and also to do field wind shear tests, right? Because that's the only way to really get your peak and residual shear strength profiles, the sensitivity values. Undrained shear strength समझ नहीं आएगा if you don't do all of this. So that's the case we made. Again, I don't know how NHI will actually do it, but this is what we explained. And we also said that once you have your forensic investigations in place, you get your real data, you may need to redesign and you may need to add ground improvement. This is a huge problem. Huh? The NH66, this is 500 kilometers, 18 packages which are under construction right now. So already out of 400 structures, 100 structures have been built and dozens of structures are under construction. So these are two failures which have already happened back to back. But the others are also very likely to fail. So for the country, it's I don't know, you're smiling, but I am very disappointed because I think as a country, this is just showing us how bad things have become. You know, so it's really bad. So we gave them an approach, and the recommended approach which we recommended was we said that first approach is because we don't have time. May में बारिश शुरू हो जाएगा केरला में. So we said we don't have time and we have to look at. They were talking about 1,500 boreholes to be done. So we said 1,500 boreholes cannot be done in 4 months. Right? Impossible to do it and impossible to do it with quality. So we made a case. We said, hey, it makes sense since we don't have time also. Do a 2-phase investigation program. And the first phase, we do CPTs at every location, starting with the locations which are built or under construction. We'll do CPTs. We can quickly look at the CPT data, cross-correlate with the earlier report. अगर match करता है तो ठीक है. अगर match नहीं करता है, that means you can't trust the earlier report. You have a low bearing capacity value. In that case, you should do a detailed design at the same location, including field wind shear test, and then do a redesign, complete redesign. So this is how we suggested, because we told them कि if you do, incidentally, even the IS code, कोई पढ़ा नहीं IS code को, but even IS code for RE wall structures clearly says that you have to test up to 30 meters below your RE wall, which was not done. It also talks about doing field wind shear test in CPT. Code में लिखा हुआ है, right? For these kind of soils, these are the tests which you should do. Code, in fact, also says SPT may be used with caution when it is not practically feasible to conduct field wind shear and CPT. This is our Indian code. So, Indian codes, if you read them, many of the Indian codes are very good.
Right.
ऐसा बात नहीं है. So then this is the case we made. We said that borehole data may not be reliable. Only borehole data may not be reliable because of data errors, subjectivity, low resolution. You'll need a lot of resources to do so much work which we don't have. Sample disturbance, small sample size. So ऐसे करके we made this case that you should have a holistic approach for at least the confirmatory investigation, do CPTs and field bench tests. We also worked out for them if you have to do 1,500 boreholes to 30 meters, right? So 45,000 running meter. So we also did this calculation and we showed them that if you have to do it authentically, this is the amount of lab equipment and these are the number of technicians which you are going to need to do this work in 6 months also.
Exactly. This is a
और
tremendous
और ये
task.
नहीं मतलब आप even if you add up lab capabilities of all the labs in the country, I don't think you will add up to this much.
Yeah,
With
exactly.
other
Exactly.
projects also happening. So we made this
Exactly.
case, and then we said, and finally we said that, if you use our approach, what we are saying, combination of in situ testing and boreholes, then we said, then it is possible to complete this work in time. Otherwise, ये तो आपका 1 साल में भी नहीं होएगा काम.
Hey, it is
This is
amazing to see for that much important a project how people are giving such kind of reports. I like the geotechnical investigation all become a report investigation kind of a thing.
Sir, it all starts with awareness. Honestly, it's just awareness, 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 awareness within the geotechnical fraternity, unity within the fraternity, and awareness outside of it. I think, and this is something, one or two people can't do it alone. So everyone, I think, I see 56 people here. I think all 56 of us need to leave this session and go out in the world, and we have to spread the word that, these are avoidable issues. या ऐसा नहीं है. इट इज लाइक कैसे बताऊं, इट्स लाइक आपको कोई कोविड हो रहा है, कोविड का इलाज है एंड किसी को पता नहीं कि उसका इलाज है. It is
Exactly.
that kind of a situation, right? So it's an engineering pandemic which is happening where we have the solution, we have the treatment, we have it in India, and we have it at a good cheap cost also.
Mhm.
Just because of lack of awareness, this pandemic is spreading. And it's all projects, huh, by the way. This project made it to the news. 9 out of 10 failures don't even reach the news. We get to know about it, but 90% of our failures, you don't even hear about it. It quickly gets.
Right. What we are seeing today, even the clients are like pushing up for a fast kind of a report, which could reach in time, and the permissions are given by the government to complete the project. They're not much concerned about the quality of the time is spent for such investigations. That's the irony.
It is awareness is a problem, malpractices, procurement practices, सारी चीजें हैं. But I think for the engineering community, if we all stick together, then that is key. हम सब लोग अगर एक भाषा में एक चीज बोलेंगे और क्लाइंट को बोलेंगे बॉस ये नहीं चलता है, we have to learn to say no. So if somebody tells you to do something which is not possible, we have to have the courage to say no. And this is where it starts.
Exactly. Exactly. And the client is always in the receiving side. Uh, Anyways, there is a question from Dr. Dharmin Kumar Shukla that what is the factor of safety, and he has asked it regarding to safe pile capacity in boreholes and CPT.
Same, Dr. Shukla, same. So the factor of safety is the same. So whether you're doing CFI analysis or you're doing from based on CPT, factor of safety is the same, which we consider 2.5 or 2. Same. Two.
Generally for CPT, it is 1.5. I would say, or for borehole, it is up to 3. It goes. So that's why I have asked.
Correct.
Because if it means that we can say that the reliability of the data already CPT is more reliable. It gives more degree of confidence while evaluating the data. So that's why I have asked. One more thing, sir. Very nice presentation. I have learned a lot. And this one question is some light on bridge which is being collapsing due to the failure. If something you can enlighten us, if you have some data or a study.
We have a lot of data, sir. I don't know how much I can share, but principally, right, the bridge failures which were happening like in Bihar वगैरह में जो हो रहे हैं,
Yes.
it is mostly geotechnical failure, obviously, right? So,
Yes.
वो बोल रहे हैं weak material, this and that. See, the underlying issue, again, as my understanding, and some of these projects I was not involved in, so it's my gut feeling. Uh, Piling, I think, especially board piles in sands, right? That is another epidemic which is happening, major epidemic. Because है क्या? See, if you combine poor investigation reports and poor geotechnical design with even worse construction practices, then you already are sitting on a कहते हैं ना ticking time bomb. वो कभी भी फटेगा आपके ऊपर. And यही in almost all our projects, this is the deadly combination which is happening. Investigations, as Dr. Pariyar also said, client at that stage, investigation stage doesn't give a damn. They're like, boss, बस मेरे को आप 2 दिन में रिपोर्ट दे दो किसी तरीके से. आप कुछ करना है नहीं करना है सस्ते में करो. They negotiate on running meter basis. So we have stopped participating in these kind of projects even. We say हमें नहीं करना. We think if you want to treat us as consultant, you tell us the problem. Don't give me a BOQ to quote. You tell me the problem. We'll sit with you as adults. We'll work out a solution, and we'll give you the value. We'll deliver value engineering to you. But you have to listen to us. Right?
Yes.
So I think we are trying to change the approach. Right? जब तक आप engineers को engineer की जगह आप ठेकेदार की तरह treat करेंगे, तब तक तो आपको कभी कुछ सुधार नहीं होएगा. So that is in the investigation stage. In the piling stage, the problem is the piling also many issues. Number one, agencies का issue same. So everybody who had little bit of money lying around, उसने piling machine खरीद के लगा लिया है. Right. So these are non-technical people. 90% are non-technical people who are the business owners. Right. So so that skill is not there. See, buying equipment, anybody can buy an equipment, but you have to have knowledge and skill to deploy that equipment and actually use it properly. वो है नहीं. तो वो
Yes.
खरीद के डाल दिया. You are completely based on the operator. Second is L1 पे काम उठाया है. तो कॉस्ट कटिंग भी चल रहा है साइट पे, राइट? हाँ, तो वो 30 मीटर पाइल है, वो बनाएगा ही, उसको 25 मीटर बनाएगा, बाकी 5 मीटर का पैसा बांट लेंगे आपस में. दिस इज ऑल्सो हैपनिंग. सो मेनी प्रोजेक्ट्स वो पाइलिंग हो गया एंड दे कॉल्ड अस, वी डिड सम एनडीटी टेस्ट लाइक पैरेलल सेismic, एंड मेनी प्रोजेक्ट्स वी हैव रियलाइज्ड कि पाइल है ही नहीं. ऊपर कैप है, उसके नीचे पाइल ही नहीं है.
Yes.
So this is the level of corruption also which is happening. The third issue is, even if chalo agency is good, and recently we were on the news for a big project, a semiconductor project in Dhulera. Good project, right people, right contractors. Okay, but even then failure happened.
Yeah.
So in that case, 20,000 piles failed, and they had to move the entire structure. Now, why that happens is the QA/QC practices are not in place. So board piles are very tough to make properly in alluvium, especially below the water. So if you don't have the right QA/QC process in place, you're not doing the third-party testing. Pile का testing piling contractor के scope में डाल देते हैं हम लोग. In most Indian contracts, which is ridiculous. It's like, if the students are allowed to check their own exam papers, तो सबका A grade ही आएगा. तो वैसा वाला situation है. So I think all these practices, and they're very easy to change these practices. कुछ पैसा नहीं लगना है, सिर्फ you have to change the way in which you work. That's all.
Thank you, sir.
Thank you.
Yes, sir. Thank you, Dr. Dharmin, and thank you, Dr. Sorabh Gupta, for a very
Mister,
insightful
sir, मैंने PhD नहीं करी.
Sir, good morning, sir. I want to ask a question, sir.
Yes,
Sorry, sir. सर, मैं यहाँ जैसे जल जीवन मिशन में हूँ, ये इंडिया में चल रहा है, तो यहाँ ओवरहेड टैंक्स बन रही है. तो इसमें जो एजेंसीज हैं जो जियोटेक इन्वेस्टिगेशन परफॉर्म कर रही हैं, कोई एक बोरहोल डेटा प्रोवाइड करता है, कोई 3 बोरहोल डेटा प्रोवाइड करता है. तो सर, एक ओवरहेड टैंक्स के लिए जनरली मान लीजिए 100 KLP है, तो कम से कम कितने सारे डेटा प्रोवाइड करने चाहिए?
ओके, तो इसके हिसाब आपके क्वेश्चन के क्वेश्चन एक ही जवाब दो देता हूँ. फर्स्ट इज यू आस्क कि व्हाट इज नंबर ऑफ बोरहोल कितना होना चाहिए. जब मेरे को पढ़ाया गया, डॉक्टर शशि गुराटी ने पढ़ाया था जियोटेक्निकल, उनने मेरे को एक बड़ी सिंपल चीज सिखाई थी. उनने कहा था किसी भी साइट पे चाहे तुम जो भी बना रहे हो, कहते हैं कि एक बोरहोल की बेसिस पे आप कभी कुछ डिसाइड नहीं करना चाहिए. तो सिंगल डेटा पॉइंट, एक पॉइंट से तो आप लाइन भी नहीं खींच सकते, हम उसमें आपकी फाउंडेशन क्या डिजाइन करेंगे। तो ये बड़ा एक सिंपल मेरे को कॉन्सेप्ट सिखाया था। सो द आंसर, माय आंसर, आई थिंक इवन व्हाट द कोर्ट मैंडेट्स इज मिनिमम 3 boreholes or test locations you should have per overhead tank to really understand. Sometimes you may have even in a small tank, sir, कभी-कभी ना lateral variation भी हो सकता है. So that is the first reason of having multiple points. Second reason is अगर आप multiple test करते हैं तो you should also compare to make sure the data is consistent. तो वो जो human error के चक्कर में गलती होने का चांस है वो थोड़ा कम हो जाता है. It's like a repeat test. तो कम से कम 3 borehole, 2 से 3 borehole तो करने चाहिए. दूसरा चीज, आप जो प्रोजेक्ट मेंशन करे मिस्टर यादव, उसमें ध्यान सिर्फ क्वांटिटी पे ना दीजिएगा, ध्यान ये भी दीजिए कि जो एक भी बोरोल कर रहे हैं वो साइट पे सिर्फ रनिंग मीटर गिन रहे हैं या उसमें एक्चुअली एसपीटी ढंग से करा जा रहा है. आर दे यूजिंग ऑटोमेटिक ट्रिप हैमर, आर दे डूइंग एसपीटी एनर्जी मेजरमेंट, आर द सैंपल्स बीइंग कलेक्टेड प्रॉपर्ली, लैब में कोई विटनेस कर रहा है कि नहीं कर रहा, कि सारे लैब टेस्ट हो रहे हैं ठीक से, एनेबल है कि नहीं है. ये सब चीजें देखना मेरे ख्याल से ज्यादा ज्यादा जरूरी है, क्योंकि अगर 3 बोरोल भी हम गलत कर रहे हैं तो उससे अच्छा ना ही करें, बेटर है.
जी सर, थैंक यू.
थैंक यू.
If there are any other questions from the participants, they are free to unmute themselves. Sir, I don't think there's anything else.
Thank you.
Okay. So with this, I'll thank you, Mr. Sorabh Gupta,
Thank you, sir.
for a very insightful session. And I'd like to invite our second speaker of the day, Dr. Abhishek, to please come on the stage.
Yes, Dr. Parihar.
Yeah, sir, before you start, I'll love to give a short description of yours, the participants. So telling a brief about Dr. Abhishek Sakleshpur. Dr. Abhishek obtained his BE and ME degree in civil engineering from Andhra University, Visakhapatnam in 2014, and in PhD in geotechnical engineering from Purdue University, USA in 2024. He's currently working as a geotechnical research engineer with Cengrs Geotechnica Private Limited in Noida. During his academic and professional career, Dr. Abhishek has worked on different topics such as CPT testing, shallow and deep foundation design, MSE walls, and bridge abutments, and has published more than 40 technical papers in national and international journals of repute. He has received several honors and awards as well, such as the ADSE Burns Case Memorial Scholarship, DFI Gobel Rochette Dickens Scholarship, and Gerald and Bellin Reynolds Fellowship from Purdue University. Besides academia, he has also been involved in sports at a greater level. He has represented India internationally as a tennis player in the Junior South Asian Games and Junior Davis Cup also. So he has a very versatile career overall. I congratulate you first of all for having such a great career in both the fields. And with this, I'll hand over the stage to you, sir.
Thank you, Dr. Parihar, for the kind introduction. So in this presentation, we'll look in detail about the CPT, its methodology and its applications. So the topics that we'll cover, first we'll look at the cone penetration test with pore pressure measurement, so CPTU, how the test is performed, what are the test equipment, advantages and interpretation of test results. Then we'll move on to the seismic cone penetration test, which Mr. Sorabh Gupta mentioned, and we'll look in detail about that. Then we'll look at some applications of the CPTU and seismic CPTU, followed by 3 case studies, illustrating how we can use these tests in our projects. So first, starting with the electric cone penetration test with pore pressure measurement, so CPTU. So as Mr. Sorabh Gupta mentioned, we basically have an instrumented cone with a load cell inside the cone that measures the cone tip resistance, QC. Then we have another load cell that can also measure the sleeve friction, Fs, which is nothing but the shear force acting along the cylindrical portion of the sleeve. Then the cone can also measure the pore water pressure during cone penetration, which is U2. It also has additional sensors to measure the inclination of the cone during penetration, as well as when we look at the seismic CPTU, a seismic module that can also measure shear wave velocity. Now, this instrumented CPT probe is attached to the end of a string of rods. And these rods are connected one on top of each other. And there is either a CPT rig or a truck that can push this entire system down into the ground. Now, the rate of penetration is typically 2 centimeters per second. And as the cone is pushed into the ground, we can obtain continuous profile of the cone tip resistance, as you see in red, sleeve friction, as well as pore water pressure. Now, we have a code of practice for subsurface investigations for foundations, but we also expect a separate standalone code for the CPTU to come out soon by the BIS. In terms of the pushing equipment, so we basically need a hydraulic pushing unit, a series of push rods. Here we can see the CPT probe or the cone penetrometer. And then this is an expanded view of the penetrometer showing the various measurements that we can get during the test. So this is a video showing the penetration of the cone into the ground. So basically, as the cone penetrates different soil layers, you can see we measure the cone tip resistance, sleeve friction, and pore pressure while obtaining continuous profiles of these parameters in real time in the field. And so as we transition from one layer to another, you can see the change in the resistance. For example, low cone tip resistance, where you might expect soft clay, increasing to higher cone tip resistance in competent layers. Now, the systems that we can use to push the cone into the ground, so one of them is anchored trailer-mounted pushers, as you can see in the photographs here. So the source of the reaction for pushing the cone into the ground comes from augers. So we have to pre-install augers into the soil, and then the pull-out capacity of the auger is what provides the reaction to push the cone into the ground. Another type of pushers are ballasted crawler-mounted pushers, where the reaction force comes directly from the self-weight or the dead weight of these pushers. And these pushers, dead weight is typically about 20 tons. So the push capacity also corresponds to a maximum of 20 tons. Now, the main limitation with the CPT is that penetration can be restricted where you have dense gravelly soils or highly cemented soil layers. The CPT cannot be used in rocky or bouldery formations for obvious reasons, because it's difficult to push the cone in such ground profiles. But as we'll see in the following slides, the advantages of the CPT technology far outweigh some of these limitations. So what is the CPT advantage? In a nutshell, the CPT advantage is that it's cheaper, faster, and better. So it is fast because the rate of penetration is 2 centimeters per second, which means that you can complete a 30-meter CPTU sounding in just half an hour. The data is continuous or near continuous data, as Mr. Sorabh Gupta mentioned, at a depth interval of 1 centimeter. The data is highly accurate, and the electrical measurement of the cone tip resistance is continuous, and the data is recorded automatically in digital format. The CPTU is versatile because we can measure as well as interpret several different geotechnical parameters that can be used in foundation analysis. It is possible to perform the CPTs to deeper depths, almost up to about 100 meters, where we have soft clays, for example. The CPTU is reliable because you can get repeatable data irrespective of the contractor, the operator, or the equipment used to perform the test. You can get soil sampling with specialized CPT samplers called MOSTAP samplers, which we'll see in the following slides. The CPT is modular, so it can be combined with various other sensors. For example, the seismic module that we will see, an inclination sensor, and as well as in some cases, thermal sensors for measuring temperature, or even adding some cameras to visually see the ground. The CPTU is safe in comparison to the SPT in the sense that there are no drop hammers or rotating parts involved. The test is clean because there is no need to drill a borehole, so no drilling mud or muck is involved. And as Mr. Sorabh Gupta mentioned, the test is cost effective in that it is not much more, or it is comparable to the cost of conventional boreholes. So these are some typical CPTU plots. So first, if you look at the soil profile over here, we can see that there is firstly a clean sand layer where you have high cone tip resistance because it is difficult to penetrate the cone in such layers, so the resistance is much higher. As well as if you look at the pore water pressure, now the measured pore pressure, which is U2, matches with the hydrostatic pore pressure indicated by the dashed line. And this hydrostatic pore pressure simply depends on the depth of your groundwater table. Now, if we come deeper where we have a soft silty clay layer, you can see that the cone tip resistance drops dramatically to very low values in the soft clay layer. And this is accompanied by a spike in the pore water pressure, because during cone penetration, we measure excess pore pressure in the soft clay layer due to the low hydraulic conductivity of this layer. And the advantage of the cone CPTU is it can delineate even the smallest or thinnest horizons in the ground profile that may be missed by the SPT. And to illustrate this point, this is an example from one of the sites here in Noida. So here, board cast in situ piles were already installed, and we did pile integrity tests on these piles. And what we found is that on some of the piles, there was a defect in the pile shaft, particularly necking, at a depth of about 21 to 22 meters. Now, when we went back and we looked, we performed CPTUs and we looked at the cone tip resistance, what we found is you can see that there is a sudden drop in the cone tip resistance exactly at the depth where this necking was observed. And this was attributed to the presence of an underground stream that was going at around that depth in the ground. If we look at the SPT N values at the same depth, the numbers are hard to read, but basically SPT N values show around 75, 80, and 86 at the same depth. So clearly the SPT was not able to capture the presence of this thin, weak layer, which contributed to this defect in the pile shaft. Now, the CPTU data is repeatable. This is an example from Professor Peter Robertson showing two CPTs that were performed 1 meter apart, and you can see that the data overlap with each other quite well. In terms of identification of the soil type from CPTU, so using these soil behavior type charts, where on the x-axis we have friction ratio. Friction ratio is nothing but the sleeve friction divided by the cone tip resistance. And on the y-axis, you have the cone resistance normalized by a reference stress. Now, after performing the CPT, depending on where the data points plot on the soil behavior type chart, we can classify the soil as if the points plot in zone 4, for example, then it's likely to be a clay silt to silty clay type of soil. On the other hand, if the data points plot in zone 6, then it's likely to be a clean sand to silty sand. And this CPTU-based soil behavior type profile matches quite well with adjacent ground stratigraphy that is obtained from boreholes, as we can see here. Now, in addition to performing the CPTs, it's also possible to collect soil samples without the need for any additional mobilization of other rigs on site. And so the way we can do this is through a MOSTAP sampler. It's a piston type sampler where once the cone is pushed to the required depth, the cone is left in place while there is a hollow barrel that is then advanced beyond the cone into the ground. And as the soil sample is retrieved into this barrel, we can then collect it and bring it all the way back to the ground surface and take it to the lab to perform soil classification tests, index tests, even strength tests, such as direct shear or triaxial tests. This is a photograph of how the MOSTAP sampler looks like. So the sample dia is typically about 46 millimeters or 66 millimeter diameter samples. Sample lengths range from about 0.5 meter to about 1 meter. So that was about how the CPT is performed, the different equipment involved, and the types of parameters that we can measure. Now we look at how to interpret the CPT data. Now, this is the Guide to Cone Penetration Testing, the 7th edition by Robertson and Cabal. And we can estimate a number of geotechnical parameters from the CPTU that can be used in foundation analysis and design. All the equations are listed on this slide, but we'll look at each of these parameters one by one. So firstly, the raw data that we get from the CPTU includes plots of the cone resistance, sleeve friction, friction ratio, which is nothing but sleeve friction divided by the cone resistance, expressed as a percentage, and then the pore pressure. Here in the pore pressure, so the black solid line is the measured dynamic pore pressure during the cone penetration test, whereas the blue line is the hydrostatic pore pressure based on the groundwater table. Next, we have a plot of the soil behavior type, the normalized soil behavior type as per Robertson 1990. So here in this case, we can see that the upper soil layers up to about a depth of 5 meters or so consist of fine-grained soils, so clay silt to silty clay kind of materials. And then below a depth of 6 meters, we have a sand layer, sand to silty sand. So as I mentioned previously, so in the upper layers where you have the fine-grained soils, you have low cone tip resistance, increasing to higher values in the sand layer. Now we can estimate or interpret a number of other parameters from the CPTU. So the first being the SPT blow count, M60, corresponding to 60% energy transfer. Now, the scatter points that you see here are the measured SPT N60 values using an automatic trip hammer and with SPT energy measurement, whereas the black solid line is the equivalent N60 from CPTU using a CPT N60 correlation. And here we can see a good match between the correlation and the actual SPT N60 values. Similarly, it's possible to obtain an estimate of the bulk unit weight and compare that with what we get from boreholes and laboratory testing. Undrained shear strength in fine-grained soils. So wherever you see some gaps in the profile, It's because in the case of the undrained shear strength, it only is applicable where you have fine-grained soils. So, for example, clay soils. And so in the deeper layers where we have sand, we don't typically associate the undrained shear strength with those layers. Then we have the friction angle, and finally relative density in coarse-grained soils or sandy soils. So all of these parameters can be estimated from the CP2U. Now, those were all, you could say, shear strength parameters. Now, in addition to shear strength parameters, we can also obtain stiffness profiles, modulus parameters. So the first plot is the constraint modulus, which is nothing but the reciprocal of MV, the coefficient of volume compressibility. Then you have the Young's modulus, the overconsolidation ratio in the case of fine-grained soils. So here we can see a pretty good match with the laboratory measured OCR values from consolidation tests and the CPTU interpreted OCR. When we perform the seismic cone penetration test, here we can get the measured shear wave velocity, which is the data points, as well as the correlated shear wave velocity from the cone resistance, which is the black solid line. And then finally, the dynamic shear modulus or the small strain shear modulus. Now, once we have all that data, it's possible for us to build a typical design profile or a section profile. So what that means is you can divide your cone resistance profile into a number of layers or sublayers, as we have done here. And for each layer or sublayer, we can then tabulate the relevant geotechnical parameters of interest. So, for example, cone resistance, the hydraulic conductivity or permeability, N60, Young's modulus, relative density, friction angle, constraint modulus, dynamic shear modulus, undrained shear strength, OCR, unit weight, and so on. So this kind of provides a summary of all these parameters that we can use later on in design. Now let's move on to the seismic cone penetration test, which is termed SCPTU. So as Mr. Sorabh Gupta mentioned, why do we need seismic tests? First of all, as we can see this figure here on the right, 75% of our population here in India is in seismically active regions. So seismicity is a critical point, and 59 to 61% of our land mass is under seismic risk. Now, the new IS 1893 Part 1 code mandates the determination of seismic site class. In addition, we need seismic tests for liquefaction evaluation, so factor of safety, liquefaction-induced ground movements. Also, seismic tests can be used for static analysis of foundations through an estimate of the Young's modulus, or dynamic analysis of machine foundations through an estimate of these dynamic soil parameters. And another feature of seismic tests is we can use them to identify cementation or aging effects in the soils. This is an excerpt from the section 6.2.3.1 of the new IS 1893 code, which mandates the need for shear wave velocity testing for site class assessment. So in this table, we can see that based on the weighted average shear wave velocity within the depth of influence of the foundation, the site is then classified based on these 5 site classes. So if your weighted average shear wave velocity is less than 180 meters per second, for example, it falls under site class E. And according to the IS code, it means that you must do ground improvement if your site falls in site class E. Similarly, for other range of VS values, as we see in this table here, it's classified into these other categories. In addition, the shear wave velocity is mandatory for all earthquake zones. So going from zones 2 to 6 for example, as well as in various categories of structures, particularly important structures, critical structures, and special structures in these zones. Now, in terms of the depth of investigation, even the code mentions that it should be taken as the depth of influence that is specified in this table over here. So for open foundations, shallow foundations, the minimum depth of investigation is up to twice the width of the foundation measured from below the foundation base. Whereas in the case of pile foundations, the minimum depth of investigation should be equal to the length of your pile plus 2 times the pile diameter, as specified here in the code. And then there are other guidelines for pile groups as well as well foundations. Now, there are a number of techniques that are available to determine the shear wave velocity. Basically, they can be categorized into invasive techniques or non-invasive techniques, as we saw in the previous presentation. Here, we'll focus only on the seismic piezo cone test, so SCPTU. So the seismic cone penetration test works in a similar way to the conventional CPTU. The only difference is that we can attach a seismic module to the CPT probe, and this seismic module contains geophone receivers that can detect the arrival of shear waves. So usually there is a source for the shear waves on the ground surface, typically in the form of a shear beam. So when we strike the shear beam, the energy or the waves that are generated from that impact travel all the way down into the ground up to the seismic module at the required depth below the ground. And so shear wave velocity simply depends on the time it takes for the waves to arrive, as well as the distance between the impact and the CPTU or the seismic probe, because shear wave velocity is simply distance by time. So the test can be performed typically at 1 meter depth intervals, and so then you can obtain a plot of the shear wave velocity with depth, which provides a direct measure of the ground stiffness. And the seismic cone penetration test is specified in these ASTM standards, so D5778 and D7400. The advantages of the seismic CPTU is that in addition to the cone resistance, sleeve friction, pore pressure, we also get the shear wave velocity. So holistically, it covers both strength, stratigraphy, and stiffness, all in one test. So we can get high resolution profiling of these measurements, and we can detect subtle changes in the stratigraphy that may be missed by conventional spaced boreholes. The shear wave velocity, as we saw, is important for site class assessment, can be used in foundation design and liquefaction assessment. And the advantage of merging two tests, so your conventional CPTU with seismic capability, means faster data collection, fewer mobilization of additional rigs or other tests, and more robust results. Now, the source to generate these seismic waves is in the form of these pendulum hammers. So basically what we do is we lift the hammer up to a certain height and we let the hammer drop. So when the hammer strikes this shear beam, it generates the seismic waves that then propagate into the ground. So this sketch illustrates the propagation of these seismic waves. So typically the seismic module has 2 geophone receivers or 2 sensors, a top geophone receiver and a bottom geophone receiver. So the top geophone receiver will detect a seismic wave indicated in the blue color over here, and then the bottom geophone receiver will detect another seismic wave, which is shown here in red. So as the blue seismic wave, as we know, will arrive faster than the red seismic wave. And so you can see that here in the seismogram plots. The shear wave velocity is basically the difference in the distance, so S2 minus S1, divided by the difference in the arrival times between the red wave and the blue wave. Once we get the shear wave velocity, we can then calculate the dynamic small strain shear modulus through elasticity theory using this equation here, where rho is the bulk density of the soil. Now, here on the top right, we can see some seismograms at various depths. Now, what I want to point out here is the numbers are hard to read, but on the x-axis, we have the time in units of milliseconds. Now, here in this example, the difference in the distances is about 0.5 meter, and the difference in the arrival time of the waves was about 3 milliseconds. So when we take the ratio of the two parameters, we get a shear wave velocity of about 150 meters per second. All these seismograms were, in fact, the tests were done at the same depth. And so we obtained consistent results at the same depth, showing the repeatability of the test. It's important for you to keep in mind that the shear wave source plays a crucial role for the quality of the seismograms, the efficiency of the shear wave velocity measurement, the accuracy and repeatability of the data, as well as the depth up to which you can perform the test. So the quality of your wave source directly affects the depth up to which you can perform the SCPTU. Now, there are various criteria that are available to assess the quality of the seismic measurements. These seismogram plots typically consist of 3 features. So first, you have an initial silence where you're waiting for the seismic wave to arrive to the geophone sensor. Once the wave arrives to the geophone, then you can see the main S wave that is picked up by the geophone. And then as the wave passes the geophone, there is a tail that follows beyond it. So basically an initial silence before the arrival. Then you have the main shear wave, which is a high amplitude signal. And finally, a tail corresponding to medium to low amplitude of reflections and refractions. Now, the main shear wave should exhibit a consistent delay between the waveforms. So what that means is there should be a consistent delay between the blue wave and the red wave throughout the entire signal, because the shear wave velocity is directly depends on the lag between the blue wave and the red wave. Depending on the coefficient of variation of the seismic measurements, so basically your standard deviation divided by the mean, you can then assess the quality of the seismic data. So if your coefficient of variation is less than 1%, it means there is excellent repeatability. However, if it's more than 10%, it indicates poor repeatability of the data. These are example seismograms from seismic CPTUs that we did in Kutch, Gujarat. So each plot that you see on the left-hand side is at 1 meter depth intervals, so from 0 to 10 meter depth, and on the right-hand side from 11 to 20 meter depth. And by analyzing this data at every 1 meter depth interval, we can then build a profile of the shear wave velocity with depth. So here what we found was, we found a very good match between the measured shear wave velocity from the seismic cone penetration test, as well as the shear wave velocity obtained from correlation with CPTU, which is the black solid line. So from the SCPTU, you can get an enhanced ground characterization where all the parameters are in one plot, and you can then make a confident assessment of your ground profile. So here we measured actually a very soft clay in Kutch, Gujarat, up to about 18 meter depth. And then below that, we had silty sand to sandy silt layers. The SCPTU is very versatile. So you can do a dissipation test to get coefficient of consolidation and the hydraulic conductivity. You can classify the soil based on soil behavior type charts. And then you can also get the stress history, reconsolidation stress, or estimates of the overconsolidation ratio. And then from the shear wave velocity, you can get the dynamic shear modulus, small strain shear modulus. And if you degrade the small strain shear modulus, you can get the E value to use in your settlement calculations, as well as the undrained shear strength for fine-grained soils. So a number of parameters that you can estimate or determine from the seismic CPTU. As I mentioned, the repeatability of the seismic CPTU is excellent, as shown on the slide here. So shear wave velocities of on the order of 216 to 217 meters per second. Each number corresponds to a test repeated at the same depth to ensure that we are getting repeatable data at the same depth. In terms of data comparison between the seismic CPTU versus other tests, for example, the cross-hole seismic test. So here, this is an example where we did both seismic CPTUs and cross-hole seismic tests, and we can see a good match between the two results for the shear wave velocity. However, the key difference to keep in mind is, although the shear wave velocity values are comparable, you can save significant cost and time with the seismic CPTU, because with the cross-hole seismic test, you have to drill multiple boreholes. You need to have a source borehole to generate the seismic waves, and then two receiver boreholes. So borehole drilling, and then placing your annular PVC pipes, and using grout to set the pipes in place. All that takes significant amount of time and cost, which can be eliminated with the seismic CPTU. As I mentioned, with the seismic CPTU, you can cover strength, stratigraphy, and stiffness all in one test, whereas CHST lacks the strength and stratigraphy data because it only gives you shear wave velocity. So with the SCPTU, you can get faster data collection, fewer mobilization of other rigs, and more robust insights. When we compare the seismic CPTU with the standard penetration test, the key advantage is that the SCPTU, as the CPT, SPT, as Mr. Sorabh Gupta mentioned, if you use your typical Bowles correlation, correlating the E value with the SPTN value, it is typically very conservative and you get very low values of the modulus. Whereas from the SCPTU, what we found is you can get up to 2 to 2.5 times higher modulus values, which directly indicates that you were underestimating your soil stiffness. So by getting realistic values of soil stiffness, you can then justify higher net allowable bearing pressures, which corresponds to smaller foundation sizes, faster construction, and then a reduced overall cost. Now, the best practice would be to combine and cross-check. So what that means is you can pair seismic CPTUs with standard tests like SPT, the pressure meter, or cross-hole seismic test for a multidimensional site model. So the more information or data that you can have about your site, the better informed decisions that you can take, and the better you can optimize your foundation design. However, it's important to keep in mind the type of soil that you expect on site, because if you expect dense gravel or cemented soil layers, that may limit cone penetration, so you have to plan accordingly. In such cases, you could go with the cross-hole seismic test to get the shear wave velocity. And where we have seismic zones and where earthquake design is mandatory, the seismic CPTU's direct VS measurement is very valuable. Now let's look at some applications of CPTU and SCPTU. So the CPTU or the SCPTU can be used for various types of projects. So starting with pre-bid or pre-tender investigations, if you're interested to obtain a quick estimate of the ground stratigraphy and the site conditions. It can also be used for confirmatory geotechnical investigations. So, for example, if you already have boreholes that were done on site, but you'd like to validate or verify those borehole investigations, so this is particularly suitable for that purpose. You can also use it for detailed ground investigation and site characterization. So in addition to these 5 measured parameters, you can get a whole bunch of interpreted parameters as shown over here, covering strength parameters, stiffness parameters, as well as stress history parameters. And finally, for ground improvement control, so if you compare pre-ground improvement and post-ground improvement CPT data, you can then attempt to quantify the degree of ground improvement that was achieved. So other applications of CPT results, so foundation design, so we can use the CPT data to estimate bearing capacity and settlement. Typically, these design methods can be classified into direct design methods or indirect design methods. In these direct design methods, you directly use the cone resistance, for example, to estimate bearing capacity or do settlement calculations. In the indirect methods, what you do is you use the CPT data to estimate shear strength parameters, such as your C5 parameters, and then calculate bearing capacity using your conventional bearing capacity equation. Deep foundation design, so axial capacity, lateral response of pile foundations, liquefaction analysis, so calculation of your CRR and your factor of safety against liquefaction, and ground improvement control, as I mentioned earlier. So all these applications can be done using CPT results. This is a slide comparing liquefaction susceptibility analysis with the CPTU on the left and the seismic CPTU on the right, done at the same location on the same site. So here, this is an example showing the excellent comparison of the depth to liquefaction. So from the CPTU, we estimated 5 to 8 meters, whereas the seismic CPTU indicates 6 to 8 meters. So this cross correlation or this additional corroboration can give you better confidence in your liquefaction susceptibility assessments, all in one test. In terms of assessing ground improvement efficacy, so here the black solid line are CPT results before doing ground improvement. And then after doing the ground improvement and doing post ground improvement CPTs, you can see that there is an increase in the cone resistance. The relative density has increased due to the densification produced by the vibroflotation technique that was used here. An increase in the friction angle as well as an increase in your Young's modulus profile. So the CPT is particularly advantageous to for QA/QC of ground improvement. In terms of using shear wave velocity in your static or dynamic analysis of foundations, so basically the key link is from shear wave velocity, you can get your dynamic shear modulus or the small strain shear modulus. And then from here, you can go to your dynamic Young's modulus. And then if you degrade your dynamic Young's modulus using your Lusitic-Dobry type of degradation curves, you can then get the E value to use in your settlement analysis, in static analysis for foundations. Identification of cemented soils. This is a topic of ongoing research, but I'll just briefly touch on it to give you an idea. So basically, the cone resistance is a measure of the large strain soil strength, whereas shear wave velocity is a measure of the small strain soil stiffness. When you combine the two together, and when we have this kind of a chart, which comes from Robertson 2016. On the y-axis, what we have is the normalized cone resistance, QTN, which is given by the equation here. So it is the cone resistance normalized for overburden pressure or effective stress. On the x-axis, you have this parameter IG, which is nothing but your small strain shear modulus divided by the net cone resistance. The net cone resistance is your total cone resistance QT minus the vertical total stress. Now, Robertson identified different zones on this chart through a parameter KG star, which is given by the equation shown over here. Basically, if your data points plot within the band bounded by kg star values of 100 and 330, it indicates that you have young uncemented soils in your soil profile. But if your data points plot above this upper bound value of 330, it indicates that your soil profile has cementation or microstructure or is significantly aged, and it's not a young deposit. So through this parameter, so if it's less than 330, so your soils are likely young and uncemented. More than 330, it indicates significant microstructure. And the higher the value of this particular parameter, the more the degree of cementation or aging that is likely to be present. An important note to keep in mind is that traditional CPT-based correlations have been typically developed based on a database of young, uncemented, or unstructured soils. And so in certain cases where your site consists of structured or cemented or aged soils, it may be important to develop local or site-specific correlations when interpreting the CPT data. Now, to illustrate this point, this is an example from, again, from Kutch, Gujarat. So on the left-hand side is a seismic cone penetration test, SCPT 101. And you can see that most of the data points plot much higher than the upper bound value of 330 for this kg parameter. And so it indicates some cementation or aging effects in the ground profile. Now, when we looked at the shear wave velocity with depth, you can see that based on the correlation, the black solid line produces lower shear wave velocity below a depth of 5 meters. But the measured shear wave velocity from the seismic cone penetration test is much higher. So this clearly shows that below a depth of 5 meters, that you have some cemented soils or aged soils in the lower half of your ground profile, whereas in the upper half of the profile, it's likely more young, recently deposited soils. Now, on the right-hand side, it's another example where you have an excellent match between the measured shear wave velocity and the interpreted shear wave velocity throughout the entire depth. So this indicates that there is no evidence of cementation here. And when we plot the data points on this chart, we see that it falls within the range of values where we expect no cementation to exist. How can this be used in your design? So for example, if you're doing a liquefaction analysis and you see that there is considerable cementation here in the lower half of the profile, you could consider using an aging correction factor on your cyclic resistance ratio, for example, when you do liquefaction analysis. So that's an example how you can make better decisions by using advanced in situ tests. Now let's look at some case studies where we used these tests in our projects. So the first case study is a pre-bid or a pre-tender investigation for a major bridge across the Ganga River in Patna, Bihar. So here the client was interested to obtain a quick estimate of what the ground stratigraphy was and the site conditions. So here, this is for abutment A1, where we did one borehole and then 4 CPTUs. In terms of the site stratigraphy, the stratigraphy from the borehole data matched quite well with what we got from the CPTU. So in the upper half, all the way up to a depth of about 25 to 30 meters, we had soft, fine-grained soils, so clayey silts. And then as we went below 25 to 30 meters, we had medium dense to dense fine sand. If we look at the cone resistance, we can see that very low cone resistance values up to about 25-meter depth, and then the cone resistance increases when we get into the medium dense to dense sand layer at the bottom. When we cross-correlated the measured N60 values from the SPT, which are the data points, and the CPT interpreted N60 values through correlation, which is the continuous solid line, we found an excellent match between the two. And so when we did calculations for the pile capacities, what we found is that from boreholes using your conventional C5 analysis as per IS 2911, we got an ultimate pile capacity of about 12.8 meganewtons, whereas using the CPTU Robertson design method, we found a total pile capacity of about 17.6 meganewtons. So this was for board cast in situ piles placed up to a depth of about 35 meters below the ground surface. And so by using the CPTU, we obtained 38% higher pile capacities as compared to the conventional borehole approach. And so this then allowed the client to optimize the foundation length and optimize the foundation cost. Another case study where we did a detailed ground investigation and site characterization was for high-rise group housing project in Sector 104 in Gurgaon. So this was high-end high-rise towers of about 40 stories. So 5 towers of 40 stories and 2 towers with 30 stories with 3 basements. And it also included a commercial building and other facilities. So here the scope of the work included a hybrid approach where we did a mix of boreholes, SPT energy measurement, CPTU tests, pressure meter tests, as well as cross-hole seismic tests. So as Mr. Sorabh Gupta mentioned, this was like a gold level geotechnical investigation that was done here. In terms of the borehole profiles and the strata interpreted from the CPT, so the stratigraphy, because it's in the Indo-Gangetic plains, the soil profile consisted of sandy silt of low plasticity with intermediate silty sand zones. Groundwater was met at shallow depth of about 3 to 6 meters below the ground surface. These are the CPTU plots. So this is the average of the results across the multiple number of CPTs that we did at the site. So your typical cone resistance, leaf friction, pore pressure, friction ratio, and your soil behavior type. These are the various interpreted parameters as we saw earlier. And we also overlaid the results of laboratory tests on the CPTU interpreted parameters, and we found a very good match between the two, providing additional corroboration and confidence in the measurements. Again, these are constraint modulus, Young's modulus. Here, particularly, again, I want to emphasize that if you look at the square data points, they are from the SPT N value using your Ball's correlation, for example, to get the Young's modulus. Whereas if you do CPTUs, pressure meter tests, and cross-hole seismic tests, we obtained much higher values for the Young's modulus as compared to what we got from boreholes. Shear wave velocity, again, a good match between the measured shear wave velocity from crosswall seismic test and the CPTU interpreted shear wave velocity. So here, in terms of the foundation type, so both for isolated foundations as well as large raft foundations, we did bearing capacity analysis at various foundation depths, ranging from 12 to 16 meters. If you look at your conventional C5 bearing capacity analysis as per IS 6403, so the net safe bearing capacity was in the range of about 30 ton per square meter, going up to about 50 ton per square meter for these types of foundations and at these foundation depths. Whereas when we did the analysis using CPT and the pressure meter, we obtained much higher net safe bearing capacity values. And this corresponded to an increase in the SBC of about ranging from, I would say, 50% all the way up to about 80-90% or so. Now, obviously, it's not only important to do bearing capacity analysis, but also important to do settlement analysis, because then your design net allowable bearing pressure is the minimum of what you get from the two analysis. Here again, when we computed the net bearing pressures for 50 millimeter settlement, so your conventional approach based on the immediate plus consolidation settlement versus advanced testing using CPT and pressure meter, again, we obtained higher net bearing pressures through advanced testing, ranging from 60% going up to as much as 100% and beyond. Now, we also did calculations for the safe pile capacities for 100 millimeter diameter board cast in situ piles. So the pile lengths ranged from 26 meters to 32 meters below the cutoff level, which was at 12 meters below the ground surface. Again, we found that with the help with advanced testing, we were able to justify higher pile capacities ranging from 60 to 80% as compared to what we got from the conventional C5 approach. So how does this all translate into time and cost? So as Mr. Sorabh Gupta mentioned, we were able to increase the SBC by about 88% through advanced geotechnical investigation. And we were able to eliminate a piled raft foundation system and go with a pure raft foundation. So this reduced the construction time by about 2 to 3 months. And because the piles were completely eliminated, we were able to reduce the piling cost and also save on the carbon footprint. And in terms of the overall cost of the foundation, we were able to achieve about 16 crores in savings in foundation cost just by improving the scope of the geotechnical investigation. And this turned out to be a return on investment of 3,600% from good geotechnics. The last case study, which I will close with, is a confirmatory geotechnical investigation and liquefaction susceptibility assessment for the Palasbari-Solkochi Bridge in Guwahati, Assam. So here, the boreholes were already done on site by another agency, and we were called in to do seismic cone penetration tests for confirmatory work and also to assess the liquefaction susceptibility at the site. Now, because this is in Guwahati, Assam, as per the new IS code, this falls in zone number 6. So with an earthquake magnitude of about 8 and a peak ground acceleration of about 0.5 G, if I'm not mistaken. So liquefaction is particularly critical in the northeast part of India. Site stratigraphy interpreted from CPTU. So we did 5 tests here. So we obtained comparable stratigraphy from the various tests. So in the upper part, we again found silty clay silt kind of materials transitioning to sandy soils as we went deeper into the soil profile. Shear wave velocity, again, we found a good match between the measured shear wave velocity from the seismic cone penetration test, which are the scattered data points, as well as the CPT shear wave velocity through correlation with the cone resistance. In terms of the liquefaction susceptibility assessment, so based on the borehole, conventional boreholes, so based on the SPT, depth to liquefaction of about 7.5-meter depth was estimated. But when we did the cone penetration test and the seismic cone penetration test, we found that the depth of liquefaction was actually 5.5 meters. So this directly translates to savings in your ground improvement cost, because you don't need to install stone columns, for example, up to deeper depths. So not only was the depth of liquefaction reduced, but also when we calculated the liquefaction potential index, as well as the liquefaction induced settlement, we found that you could reduce the liquefaction induced settlement through the use of advanced testing. Or another way to look at it is the conventional SPT-based methods tend to overestimate the risk of liquefaction and liquefaction-induced settlements. So with that, I will close my presentation, and I thank you so much for the opportunity to present this with you, and I welcome any questions.
Thank you, sir. Thank you very much. You give a very good detailing of the test along with the case studies as well. So I'd like to first invite, if there are any questions among the participants, they can unmute themselves and ask the question straight away to the speaker. Okay, sir, I feel there are no verbal questions. There are a few questions in the chat box. The first question is from Mr. Chandrapal Gautam, that what are the key properties of the soil we need to test for preventing landslides in Himachal Pradesh? I think it's about investigating about the landslide in Himachal Pradesh. And what can be the advances that we need to conduct? Yes, sir.
Your voice was breaking a little bit, sir. Could you repeat the question again?
Yeah. So question is that what are the key properties of the soil we need to test for preventing landslides in Himachal Pradesh? And what can be the advanced tests that we can perform to conduct the same?
So for landslides in Himachal Pradesh, so in terms of the in-situ tests that you can do, depending on the feasibility of performing cone penetration tests in such ground conditions. So CPTU is a valuable tool that you can use, also corroborated by a few boreholes. So some boreholes along with CPTUs to get your strength parameters and your soil profile. For landslides, I would say, since it's basically a slope stability analysis that you need to do to assess whether your factor of safety against sliding is more than 1. So for your C phi gamma parameters to do a slope stability analysis, you can do CPTs as we saw today to get those parameters. And you can also corroborate your investigation with a few boreholes supplemented with laboratory testing.
Okay, the next question is from Dr. Rishi Rana. Can we do CPT test in typical gravelly sand of Himachal Pradesh?
Gravelly sands of Himachal Pradesh, most likely it would be difficult to push the cone in such soil profiles. So in such cases, the conventional borehole approach with standard penetration test, important to use automatic trip hammer with SPT energy measurement would be the way to go purely because of the difficulty in pushing the cone in such soil profiles. You can also supplement the investigation with pressure meter tests, for example, to get better strength or stiffness parameters that you can use in your foundation design. So among the various in situ tools that are available, as Mr. Sorabh Gupta mentioned, there are a number of tests that you can choose from in such profiles.
Okay. As per my experience, the pressure meter test is very least used in these areas. I think it's the better test to do because it caters both for the rocky conditions and the hard soil conditions as well.
Yes, yes.
It's very useful because it's very versatile. It's a pressure meter equipment. So that's the only test which you can use in all kinds of strata, whether it's from hard rock to soil to intermediate geomaterial. Intermediate geomaterial method, there is no other option. You can only do pressure meter. You can't do SPT, you can't do coring. So, जैसे अपना तराई area में you have highly fractured IGM kind of material. So, उसमें pressure meter becomes the only option actually. But unfortunately, it's not very common. I don't know why. But it's a good test to do. And you also, if you have retaining walls, which you have a lot of retaining walls in Himachal, for design of the retaining walls also, pressure meter data is very good because it will give you in situ measurement of K0 profile.
Yeah.
Right.
Rather than estimate, rather than guessing the K0 values, you can measure it.
Right. Absolutely agreed. Okay, sir. There is another question. That is again the same question on the same line. Should a CPT test be conducted in site to prevent landslide in Himachal Pradesh for the future monsoon period estimation? I think you answered that question.
Yes, and also if there is a risk of liquefaction or seismicity, then combining your conventional CPTU with the doing a seismic cone penetration test would also be very useful in such areas.
Right. We ourselves are also like educating many people that you are in the risk of that liquefaction because you are now we have shifted to zone 5. The entire Himachal Pradesh is in zone 5 now.
Yes.
There's high chances of liquefaction, but still many of the people are not aware of the liquefaction risks.
Yes, landslides particularly could happen either for static reasons or due to dynamic reasons. So static reasons, of course, depending on rainfall infiltration, for example, if depending on what soil profile you have, high pore pressures that reduce your shear strength could produce a landslide, or if there is in the event of an earthquake or subsequent aftershocks, that could also lead to a potential landslide. So checking for both cases is important.
Right, sir. There is another question from Dr. Kaushal Kumar. Are both downhole and crosshole tests are possible with CPTU?
So the seismic cone penetration test is essentially like a downhole type of a test. The crosshole seismic test is actually something that is different from the seismic CPT because you'd have to drill 3 different boreholes where you have one borehole as your source borehole and the other 2 boreholes are your receiver boreholes, and also to do a borehole deviation survey, making sure that your borehole alignment is as vertical as possible. So that's in the case of the crosshole seismic test. All those things can be eliminated with the seismic CPTU. So no need to drill boreholes, and your seismic wave essentially travels from the ground surface all the way down to your seismic CPT probe. So I hope that answers your question.
Right. There is another question from Mr. Akash Dinesh. The DS obtained in MASW test and CPT will be same or different, the shear wave velocity?
I think MASW, SSW, and seismic CPT, I think typically they do provide similar values of the shear wave velocity. However, I think with the MASW, SSW, there is the issue with how deep the seismic wave can travel into the ground. So there could be a depth limitation up to which you can get the shear wave velocity. Whereas with the seismic CPTU, so because it is an invasive technique, so it basically depends how deep you can push your cone into the ground and the energy that you create from your shear beam. So I would say at shallow depth, they can provide similar values, but the advantage with the seismic cone is if you can push it deeper, then you can get shear wave velocity up to deeper depths.
Right, sir. There's another question from Dr. Utpal Barua, that does CPT help in assessing the consolidation settlement?
Yes, sir. CPT does help to estimate consolidation settlements. So one of the parameters involved in the consolidation settlement analysis is the constrained modulus, which is the reciprocal of your MV parameter, so coefficient of volume compressibility. So from the CPTU data, so from your cone resistance, there are correlations available to calculate this one-dimensional constraint modulus that you can then use to calculate primary consolidation settlements. And this is covered in detail in the reference that I mentioned on one of my slides. So the Guide to Cone Penetration Testing by Robertson and Cabal, the 7th edition, has some of the details and the equations involved.
Right. Another question is from Arman Chandra Katoj, that in hill regions like Himachal Pradesh, how do you decide the depth and spacing of boreholes given highly variable strata?
I think that, sir, first would depend on the type of your project. What is the structure that you have planned to build first? The importance of the structure. So is it like a G+2, G+3 structure or a more important critical structure? That would decide the number and the spacing of your boreholes. Now, in terms of the depth of investigation, some of the IS codes give specific guidelines for the depth of investigation. What I mentioned on one of my slides in the new IS 1893, particularly because this is again in hilly areas in the Himachal region, which is prone to earthquakes. As per the new IS code, the minimum depth of investigation should be at least 2 times the width of the foundation in the case of isolated footings or rafts. Whereas if you're going for piles, then you have to go at least 2 times the pile diameter below the pile base. In terms of that's the minimum depth of investigation.
Right. I think it suffices the queries that are with us. If there are any queries with the participants, they can unmute themselves and ask to the speaker directly. Dr. Abhishek, I think we are done with the queries. So with this, let us announce the closure of the session. And I congratulate you for this very insightful lecture of yours. And hopefully in the coming days, we'll be inviting you again. We are planning like a 1 week or a half week FDP in the coming days. So we'll love to have some experts who are experts in the industry from geotechnical engineering who could explain the case studies and all to us. So with this, I thank to both the speakers of the day, Mr. Sorabh Gupta and Dr. Abhishek, who they have given their valuable time to us to explain many of the things which we do not get in our daily life to listen from.
Thank you, sir. Thank you for the opportunity, and always a pleasure to interact with students, academicians, researchers, practicing engineers, and sharing knowledge with each other. And in that process, creating more awareness of better geotechnics and improving the standard of investigations here in our country.
Okay, sir. Thank you.
Thank you,
Thank you
sir,
very
for the
much.
beautiful
Yeah.
insights.
Yes, Mr. Parmar.
I said, sir, thank you, sir, for beautiful insights.
Okay. Thank you. Thank you, sir. Okay, sir. Thank you very much. We'll announce the closure of this session.
Right.
Thank you to
Thank
all
you
the
so much,
participants.
Dr. Pariyar. Thank you, everyone. Thank you.
Thank you.
Hello.